I'm Shane Ross from Virginia Tech, and this is joint work with Abdullah Raik. We're asking a network-level question about cislunar transportation. Rather than designing one transfer at a time, can we identify the orbits that organize access across the whole system? Future cislunar infrastructure will require repeated movement between orbits under maneuver and time-of-flight budgets. Traditional pairwise design answers a very useful question. Can I transfer from orbit A to orbit B, and at what cost? But it doesn't reveal the architecture of the full transportation system. Once many orbits are considered together, different questions emerge. Which orbits provide many inexpensive direct connections? Which give efficient access to the network as a whole? Which might be best on multileg routes? And which might be the most difficult to reach? These are questions we address with an orbital network model. We work in the planar Earth-Moon circular restricted three-body problem. The key control in this comparison is that all 13 representative orbits are evaluated at the same Jacobi constant. So any differences in accessibility reflect orbital geometry rather than an energy mismatch. The orbital domain is roughly the region shown, and it includes a catalog of 13 orbits that span a broad set of cislunar geometries. The L1 and L2 orbits for cyclers that alternately orbit around the Earth and the Moon. 6 resonant orbits, stable and unstable of each of 3 different resonances, and 1 distant prograde orbit around the Moon. For each periodic orbit, we first place seed states at nearly uniform arc length spacing. At every seed, the velocity magnitude is fixed by the Jacobi constant, and we vary only its in-plane heading direction over an admissible fan given by a delta-V budget. Because the speed is unchanged, this turning maneuver preserves the Jacobi constant. The cost of a turn is just 2v sine of half the angle, but here the velocity v is in the rotating frame. We then propagate each perturbed state and represent the trajectory in a box-discretized phase space, where every voxel is a position and heading. We repeat this process over the orbit, the heading fan, and produce a forward reachable-set atlas. The backward atlas follows from time reversal symmetry. A candidate transfer from orbit A to orbit B exists whenever A's forward reachable set overlaps B's backward reachable set on a common voxel grid. Each overlap voxel provides a pair of candidate trajectory arcs. We assign it an approximate maneuver cost, a proxy cost, that involves the turn departing orbit A, the turn getting into orbit B, and then the patch point, which is a small voxel scale patching that's usually just a few meters per second. It's not the dominant in the cost. Where there's no overlap, that means there's no direct edge connecting the 2 orbits. And time symmetry supplies the reverse connection, giving the undirected network we use here. At the maximum reference budget, direct accessibility is pretty dense. Of the 78 possible total orbit pairs, 75 exist within budget. But the costs are highly structured, ranging from less than a meter per second to up to 400. You look at this graph, you see there's a darker upper left block core of relatively low-cost transfers. And then there's this exceptionally difficult block at the very end, the 2-to-1 stable resonance. So all 3 missing connections are connections to that orbit. We can now convert this into an orbital network. Each node is an orbit. We plot an edge if there's a feasible direct transfer under the selected delta-V and time-of-flight budgets. And the edge color represents the delta-V proxy cost. The reference budget we're using is about 400 meters per second max, and then the max time of flight of a sidereal month, 27.3 days. Now, all 13 orbits belong to one connected component at that, but the direct edge is often not the best way to travel. 60% of the transfers are cheaper going through a multi-leg path. And one orbit stands out as emerging as the leading hub, gateway, and relay. So what do we mean by hub, gateway, and relay? A hub is like an airport hub. Many inexpensive direct connections. We measure it with graph strength, which weights cheap links more heavily. A gateway is like a distribution center. It may not link to every destination, but it reaches the whole network at low cost. We measure that with harmonic closeness. A relay is like a mountain pass. It's the node that lies on the cheapest routes between the others. Even when direct edges exist, we measure that with betweenness. So which orbits play these roles? Here, each row is one orbit, ordered by rank, and the 3 columns are the 3 roles. Now, if you scan across the top, you're going to see that the 3-2 cycler is right there at the top, ranking first in graph strength, harmonic closeness, and betweenness. So it's simultaneously the strongest hub, gateway, and relay. The second tier is more specialized. The 5-2 unstable resonance is a strong hub and gateway, but a weaker relay compared to the 1-1 cycler. And at the bottom, there are some stable resonant orbits, with the 2-1 stable resonance last across the board. And we can also vary where we are in the budget plane, both delta-V and time-of-flight. When we do that, 3 different regimes are revealed, crossing different thresholds. Stage 1 is when all the orbits are connected, all 13 orbits, through one network. That doesn't mean that there's a feasible transfer between any 2 orbits. That comes later. We call that budget feasible closure, where every one of the 78 orbit pairs has a shortest multileg route, whose total delta-V both stay within budget. That's a stronger condition, and it's reached later, 350 meters per second or 20.5 days. Stage 3 is just direct accessibility growing as we increase past those earlier thresholds. The leadership result is also robust. Only 2 orbits ever win any of the 3 centrality measures. Under time-tight budgets, the 1-1 cycler leads in strength and closeness. As the available time increases, the 3-2 cycler takes over and dominates almost everywhere else. This gives a simple mission design interpretation. For rapid response or retasking, the 1-1 cycler is the natural candidate. For logistics, staging, and relay architectures, the 3-2 cycler is probably the better choice. Now, we only found arcs of trajectories that come close, both in position and velocity, so we wanted to look at differentially corrected trajectories that were revealed from initial guesses by this proxy. The ones I'm showing all come from the 1-1 cycler. First to the L1-Lyapunov orbit. Differential correction improves things. We go from a proxy delta-V of 4 meters per second to a corrected one of 2. Going to the 5-2 unstable resonance, we go from a proxy of 10 meters per second down to 6. And then going to the 3-1 stable resonance, the proxy calculation was 178. A differentially corrected lower to 174 meters per second. So it suggests that this screening proxy is conservative, which is a good thing. We also checked whether the multileg savings corresponded to actual differentially corrected trajectories. So this animation shows a transfer from the unstable 3-1 resonance to the lunar L2 via the 1-1 cycler. So one leg approaches the cycler and one leg departs from it. Across these representative cases, routing through the 1-1 cycler reduces the screening cost by up to 66% compared to the direct alternative. The important point isn't that the 1-1 cycler has a high graph score. Its dynamical neighborhood can function as a practical bridge between otherwise expensive endpoints. This supports the network interpretation of a relay and motivates future phase-resolved optimization of complete multileg routes, so taking into account the time that it's on the intermediate orbit. To conclude, this network perspective provides 3 main outcomes. First, it discovers a clear hierarchy among orbits. The 3-2 cycler is the dominant hub, gateway, and relay. 1-1 cycler is favored for short-time missions, and the stable 2-1 resonance remains persistently difficult. Second, it separates 3 ideas that are often conflated, which is direct accessibility, graph connectedness, and then this budget-feasible multi-leg closure we introduced. Third, the differentially corrected examples support the atlas as a conservative design screening framework, with the relay examples showing that graph-identified intermediate orbits can produce substantial savings. The natural extensions are to the spatial problem and ephemeris dynamics, and also low thrust or optimal control refinement. The QR codes link to the paper, and also, if you're interested, an interactive budget explorer. Thank you.
Hey, if you appreciated this and you'd like to see more advanced level content like this, please like and subscribe.